Okay, so welcome back to Calculus 1. And in this lecture, we're going to cover a very important notion of continuity. Now, we've sort of already kind of touched on continuity in several different ways, right? Like when we were looking at evaluating limits, some of the functions we started with were jumping around and there were holes and stuff, right? And when it didn't do that, I was calling them smooth and continuous, right? So even though I was using those words, we hadn't defined it yet. Now, in maybe college algebra or pre-cal, you might define, without calculus, you might have seen a definition of continuity that looks something like, I don't know, a function f continuous if, I think I saw a college algebra textbook define it like if you can draw the graph of f.
Professor.
Yes. Oh, thank you for calling that out. The lighting is kind of bad in here. All right, so again, that's a definition that I saw in a college algebra textbook. A function f is continuous if you can draw the graph of f without lifting up your pen. It's kind of a vague notion, right? Like, and it doesn't capture the true meaning of what it means to be for a function to be continuous. Now, from college algebra, I guess like it like sort of like makes sense, right? You can just anything that you can do, whatever like that, it's continuous, right? But now that we know about limits, we can actually look at the formal definition of a limit. Well, a more formal definition. It's not the most formal that's available, but I would call it formal. So with calculus, the definition would look something like a function f is continuous at x equals to c whenever following three properties hold. I'll just save time and just write them out. All right, so part one is that f at c exists or is defined. Part two, the limit as x approaches c exists. And then finally, part three, these two values equal each other. Okay, so this will be the notion of continuity that, or the definition of continuity that we will use in this course. Okay, now notice that there's a little bit of there's a difference, not a little difference. There is a difference between this definition of continuity and this definition of continuity. And the main difference is that this is kind of looking all over the place, right? It's like drawing the graph over some interval, right? Whereas this over here, this definition is saying a function is continuous at a point. Okay, that's a very big distinction, right? That's over some interval. This is at a point. So continuity is defined at a point. It just so happens that if f of x is continuous at every point in some open interval AB, then we write that f is continuous on that interval. Yeah. So this is what it means for a function to be continuous on an open interval. And that's like really important to note that this interval here is open. Okay. So this definition is for continuity at a single point, but we can extend it to an interval, an open interval, just by saying that it's continuous at each point in that interval. Okay, now in a similar fashion, if f is continuous at every point in R, then f is continuous on R. And that's like this. Right? So what are some possible like examples we should probably look at, right? Which, by the way, in any of your mathematics courses that you take, you should always try to practice the following. You encounter a new definition, give an example of what it is, and give an example of what isn't. If you can do those two things, then you probably understand the definition enough to move forward. If you can't do that, then you need to ask the instructor, what's a counterexample? What's something that it isn't, right? Or what is an example of what it is, right? And this is just good practice in all your math courses. So let's consider some examples. Example A. Maybe like f of x equals 1 over x. So let's just kind of like discuss the continuity of this function, right? So what does this function look like? Well, it looks something like this, right? Okay. Yeah. So let's first focus on continuity at a point, like let's say like right here, when x equal to 1, right? So is this function continuous at x equals to 1? Well, go through your list, right? So does f of 1 exist? This is like part 1 of that list. So does f of 1 exist? Yes, right? Part 2. What about the limit as x approaches 1 of this function? Well, heading towards x from this direction, we're going to start heading towards 1, right? And then heading towards x from this direction, the function will start heading towards 1 as well, right? So this exists. Right. Again, like this is one of these rational functions that we encountered in a previous lecture, right? And the limiting value will not have any division by 0. It's good. We can just plug in the limiting value and it's done, right? So, and then part 2, it is indeed the case that f of 1 equals the limit as x approaches 1 of f of x. So these three things together imply that f is continuous at x equals to 1. All right, so again, we wrote a definition, and then we gave an example of a function being continuous at a single point. Right? Now, where is this function not going to be continuous? At x equals 0, right? At the value x equals 0, it's not going to be continuous. Why? Well, the easiest case is that right? It doesn't satisfy part 1. If we try to plug in x equals to 0, it doesn't exist. It cannot be continuous at that point. Okay, but it looks like it's continuous everywhere else, right? So it would seem that, every other choice of x is going to work. So maybe instead of just defining this one point here, we can say f is continuous on -infinity to 0 non-inclusive. This is using integral notation, union 0 to infinity. So this is the integral from -infinity to 0 non-inclusive, 0 to infinity non-inclusive. All of those x values together with that union, this function will be continuous at. Okay. So that's one way of discussing the continuity of this rational function. Okay. And again,
sorry, is that x equal to 1 limit on the third? Is that
on that side of the board, way over there? Yeah.
Yeah, I can't see that.
Yeah. F of 1 is equal to the limit of f of x as x approaches 1. So that's x going to 1 right there as well. I'll try to write bigger. Actually, I'll try to find fatter markers next time so that all of you can see better. Okay, another example. Let's look at g of x equals to, what did I have? The rational function x squared minus 1 all over x minus 1. Okay, this is just one more example to kind of nail down the definition, and then we can move on after we think that we understand it. Right? So what does this function look like? Any guesses? Well, it would help to factor it first, and then you can get a better sense of what this looks like. In particular, the numerator is a difference of squares. So we can factor the numerator. Like that. So does that give you a hint as to what the function looks like? So pretty much everywhere that x is not equal to 1, these terms are dividing out, right? So what are you left with? Just x plus 1. Everywhere other than x equals to 1, right? In x plus 1, all of you should know that. That's just a line that's been raised up by 1. So this function should look like the line raised up by 1. Like maybe like this, and then up. There's a hole there, and that hole there is because the function is not defined at x equals to 1, right? We have division by 0. So immediately, what do we know about the continuity of this function? It's not continuous where? At x equals to 1, right? However, it looks like everywhere else, it is continuous, right? Any other point that we picked, and when I say that, I'm kind of jumping ahead, but just think about it for a moment. If you're not at x equals to 1 on this graph, right? And so first off, you can evaluate the function at any of those points. So that's part 1 of this definition, right? Second, you can find the limit anywhere, right? The limit's just going to be there and like wherever, right? And then also the limits will match up, right? Like if I looked at like a half, right? X equals to a half. So it's like right here, okay? And as we're approaching x equals a half from the left, the function is going right there, right? To 3 halves. And if, as we approach x from the right, it's going to go down. There's like a hole right there, but it doesn't matter. That's not where we're going. We're going to this value right there. So the limit there is going to be 3 halves, right? And then the function's value at that point will also be 3 halves. So it'll be continuous there, and the same argument will hold anywhere else. But again, at x equals to 1, there's a problem. Because, well, it doesn't even exist there, right? But what happens if it did exist there? Let's just suppose that it does exist there at x equals to 1, right? So maybe I'm going to have to modify my example to illustrate another important point. These have been kind of easy because the function just didn't exist, like a very obvious value, right? But what about if I modify g to be, or actually I'll call it h. This will be one of these weird piecewise functions. Which is equal to x squared divided by x minus 1 whenever x is not equal to 1 and equal to, say, 1 if x is equal to 1. So this is a piecewise function, right? So now, let's look back at our graph here. The graph basically, it looks very similar, right? Because pretty much everywhere, it's that, which that's what we plotted there, right? However, now at x equals to 1, the function's value is 1. So here at 1, right there. That's the graph of this h function. So now notice that if we're looking at the definition, f of 1 exists. Right? It exists. And then for part 2, what about the limit as x approaches 1? So what's the limit as x approaches 1 of this function? On the left-hand and right-hand sides, where's the function heading? should be, so as we're heading this way, right? This is x is equal to 1. So like at 0, we're right here. At a half, we're right here. Right? At yeah, so as we just keep on getting closer, we're starting to jumble up right there as we're heading towards 1, right? And then if we're coming from this direction, different color. So at like x is equal to 2, we're like up here, and then halves. We're going this way. And then from the left-hand side, we're heading this way. We're heading to that value in the middle of them, right? So the limit here, as x approaches 1, oh, not f, h. Sorry about that. So the limit is going to be just 2, right? They're both, so I almost drew it kind of nicely here, but yeah, it's going to 2, right? We're getting closer to 2 as we head this way, and we're decreasing now towards 2 from the right-hand side. They're both going to 2, and we'll actually learn about left and right-hand side limits in a moment, but we have to really focus on this for now. But they're both going to the same place. They're going to 2, right? And we could have known that by using one of the theorems from last class, right? This function, like g, right, is equal to x plus 1 everywhere except for 1 point, which means that the limits will be the same. So we know that the limit of this here, which is, that's like the majority of it, right? Yeah, this differs from x plus 1 at 1 point. They'll have the same limit as x approaches 1. So that's like by using that theorem from last time. Now, so far we're looking at this, this definition and we're checking things off, like h of 1 exists, the limit as x approaches 1 for h exists, but is part 3 satisfied? No, right? Because h of 1 is 1, right? These two values don't equal. So it does not satisfy the definition of being continuous at x equals to 1. Even though the limit exists and you can evaluate the function there, it's still not continuous. And the reason for this is this jump, right? So this is what would be called a jump discontinuity. Okay. For g, that point right there wouldn't exist for the original function g. Then it would just be like a removable discontinuity. So it doesn't jump, it's just there's a hole there, right, where it's not defined. Okay, so this function h and the function g are continuous everywhere except x equals to 1. Okay, so let's try another one. So another example. Let's say we call it like R. R of x is equal to piecewise function x plus 1 whenever x is less than or equal to 0, and x squared plus 1 whenever x is greater than 0. So again, the piecewise functions, you always have to be very careful when you're looking at them. So far, this one was discontinuous at x equals to 1, but this one, it looks like at x equals 0, there might be something weird going on there. Maybe it's discontinuous at x equals to 0. I don't know. We'll find out. So what does this graph look like? So the graph of this thing, when I teach piecewise functions in college algebra, I tell them to draw both functions and then erase the parts where it's not defined in a certain way. So for example, x plus 1, we know what that looks like. The top part would be like this. That's x plus 1. And then x squared plus 1 is the parabola lifted up by 1. Right? So lifted up by 1. It's like this. But now I can fill it in. What lines do I draw in? Well, for the linear piece, it's whenever x is less than or equal to 0. So the linear piece will look like this. Okay. And then when x is greater than 0, it looks like the parabola plus 1. So then it'll be, it's gonna be hard to make that or something. Then I can just get rid of everything else. So that's an ugly drawing of what the function r would look like. Okay. Now, for any x greater than 0, it's just the parabola, right? So if we're strictly greater than 0, we're on this side. This is a polynomial. It's smooth. There's no holes or anything. It should be continuous everywhere past 0. And then this linear function, everything less than 0, again, same argument, should be continuous. But what about at x equals to 0? Well, again, I know I'm being repetitive with this, but this is how you analyze functions for their continuity. So part 1, what is r evaluated at 0? You look at the piecewise function, it's in this case here, right? So when x is equal to 0, it's just this part. So 0 plus 1 is just 1. So it exists. It's defined, right? So far, looking good. Part 2. What is the limit as x approaches 0 of this function? Well, if we head towards 0 from this way, right? We're going, so there, it's like we're heading towards 1, right? What about for x greater than 0, heading towards 0, right? Well, there, as we're getting closer, it looks like it's also going towards 1. So then, these two equal. So these two things together say that r of x is continuous at x equals to 0. Even though it's a piecewise function, it's still continuous. So yeah, I think this is an important thing to note. Just because it's a piecewise function doesn't mean it won't be continuous at some point. It has to do with the behavior of the limiting process together with the behavior of the function at that whatever point you have in question. So the only one that seemed like there might have been a problem with was x equal to 0, but we fixed it. We understand what happens now. So this function is actually continuous on all of R, everywhere. And kind of looking at it, you can see they both meet up at 1. The limit meets up, the limit heads towards 1 from both pieces, and the function's value at 0 is 1. Okay. All right, so I'm going to take a quick break, pause the video, and answer any. Okay, so we have, I think, nailed down at least like a little bit the notion of continuity of functions over, well, at single points and on open intervals, right? So next, we need to build up tools to talk about continuity on closed intervals, okay? So that's the question we wish to answer. But what about continuity on closed intervals? Okay. Now, to answer this question, or to define continuity on closed intervals, we need a definition. But the definition I'm going to introduce is something that we've already been talking about. So, definition. So, I'll just write it out. There's two parts. The limit as x approaches c with a superscript plus sign. Okay. Of f of x is the right-hand side limit. Okay, and what does this mean? It means, well, it's the limit of f of x as x approaches c from the right, right? So x is greater than c. So and so again, when I say from the right, I mean that the values of x that you're picking are greater than c. And you're getting closer to c from the right. Okay. Again, we've already kind of talked about this notion. Okay? And then next, the limit as x approaches c with a superscript minus sign of f of x is the left-hand side limit okay, and this is the limit as x approaches c from the left. So the x is smaller than c. Okay. Now, intuitively, we should have like already an idea about these. I'm not sure if we need to look at any examples specific to this one and then this one. I think that we'll understand them more when I define continuity on a closed interval. So I'm going to pause on giving examples now, but I will give examples in a moment. I just want to write out some more things. Okay. Now, so, okay. No, I want to stick with what I said earlier. If you encounter a definition, look at an example, like immediately. So I'm going to stick to that. So example, let's look at maybe, yeah, let's look at limit as x approaches -2 from the right of the function square root of 4 minus x squared. Okay. So let's just look at a right-hand side limit. The left-hand side limit should also work. Now, I am assuming that the majority of you will not know what the graph of that function looks like. It's sad. It's not bad, but it saddens me because it's like one of my favorite equations that you deal with in like pre-cal or even college algebra. Does anyone remember the equation of a circle? Oh, you'll have to know that one. So let me, I guess I'm gonna have to recall some things to make sure we're all on the same page. So recall a circle. Make sure my students can read this. So a circle with radius r is defined by x squared plus y squared is equal to r squared. Okay, that's the equation of a circle. Do y'all remember this, or have you ever seen it? I know for some of you, it might have been like years since you last took a math class, so I get it if you don't recognize it, but that is it. Right, that is, yeah.
The teacher teach me says x squared plus y squared equals to z squared.
That's fine.
It can be anything, right?
Yeah, it's just any variable, right? The x squared plus y squared equals z squared is actually typically used when looking at like right triangles, which there is a connection between right triangles and circles, right? So if you plot each point on, I'm actually glad that you brought that up. This famous Pythagorean theorem, right? Right. It's actually related to the points on the circle, and maybe I'll make like a little video for that. It's a nice concept. I like circles. So okay, how does this relate to that? Well, if we want to maybe look at this, there might be a relation, I don't know. Maybe instead of looking at this equation, what we can do is we can solve for y as a function of x. Okay, so if I subtract x on both sides, I get that y squared is equal to r squared minus x squared, right? And then if we're going to solve for y, we take the square root on both sides. And we finally arrive at y is equal to either plus or minus the square root of r squared minus x squared. Plus or minus when you take the square root on both sides, right? Now, these look similar, right? Like, that's what we're looking at. So maybe this is like 2 squared right there. See it? So what's happening with the graph of this is that it looks like this. It's always really hard to draw circles. I like them, still hard. Okay, so the radius of this circle is going to be what? 2, right? Because it's the 2 squared part, making the 4. So it's going to be way too fat, I think. Yeah, that's not the best. Oh, that's awful right there. Hold on. Okay, so this would be so each point on this figure would be generated by this equation with r is equal to 2. Okay. Now, when we solve for y as a function of x, like we're looking at, maybe I'll just write it out. This is positive, right? So we're looking at the positive piece of this plus or minus. So, and again, this is 2 squared minus x squared. So the positive piece will be the positive values here, right? So we can just get rid of that, get rid of this, and what we're left with is a graph of now the function that. So that's what it looks like. Now, that is a pretty good half circle. I'm excited for that. Okay, so now back to the limit, the right-hand side limit, which again, right-hand side means that as we're approaching C, we're picking x that are bigger than it, getting closer to it from the right-hand side, right? So clearly, like we can't just like plug in -2 because, well, actually, we can plug in -2, right? That's fine. But on the graph, we can see it's heading, so like, where are my other colors? So when x is equal to -1, the function's value is up there, right? Right, so it'd be √3, right? And then here, we're there, as we're getting closer, heading this way, and by the time we get there, okay, 0, right? Which maybe this wasn't such a good example. Again, I wasn't planning on doing an example right ahead, but this at least like illustrates the process and reminds you about the equations of circles. Okay, now you can imagine what would be the left-hand side limit as x approaches +2, it would also be 0, right? Okay, now, now that we more or less understand these left and right-hand side limits, we can just like write a formal theorem now, using them in the manner that we have been using them all along to talk about the limit of a function at a point, right? If we look at the left-hand side and right-hand side and they're going to the same spot, if they meet up, then the limit exists, right? So, so I'll just say the limit as x approaches C of f of x equals L, which that implies that it exists whenever I write that. if and only if and only if, which for those of you that will never take a course called discrete math, if and only if it comes from logic, and it's like an equivalence between two things. Right, so whenever you see if and only if in a mathematics course, it's equivalence between statements. Like that's a statement, and whatever follows this is going to be equivalent to it. So if and only if the limit as x approaches c on the right-hand side of f of x equals the limit as x approaches c from the left-hand side of f of x equals L. So again, statement, if and only if statements, which logically means that this is the same as that. Which is, again, kind of silly to write it now because this is kind of what we've been doing the whole time, right? We look at where the function is going as we get closer from this side, and if they meet up at the same value, then the limit exists. So that's the statement of the theorem. Okay. So now that we have left and right-hand side limits, kind of verify what we've already been doing, we can finally answer the question that I posed about defining continuity of functions on closed intervals. Okay. Mission. Okay. So f is continuous on the closed interval AB whenever f is continuous. Sorry, that's a really nice F. F is continuous on the open interval AB and let's see, the limit as x approaches a from the right of f of x equals f of a. And the same thing with b. But now we have to approach from the left-hand side because b is on like the farthest to the right on the closed interval. So we have to use x in the interval that are bigger than it heading towards it. So, or smaller than that. So heading towards b from the left. Okay, so this is what it means for a function to be continuous on a closed interval. Now, yeah. Notice there was a difference now. Oh, that's a bad term. And this is different than the continuity we discussed earlier. So actually, that example that we did over here, this function here, root 4 minus x squared, that's going to be continuous on, so this is continuous on the closed interval -2 to 2. Right? We already found the right-hand side limit as x approaches -2, which is like our A in that definition. It happens to equal evaluating this function at -2. The same thing that happened on this side for +2. And it's continuous everywhere else in there. It's continuous on the closed interval -2 to 2. That's actually a good example of what's up there. Okay. Now, as like a problem to think about, maybe something like this, like question. So is f of x equal to root 1 minus x squared continuous on the closed interval -1, 1. Okay. That's similar, right? Does anyone know what the graph of this looks like? It's a half circle again. And what's the radius of it? Just 1, right? So this will look like this. Right. And there's the graph of it. So to argue that this is continuous on that closed interval, you'd have to do a few things. Argue that it's continuous on the open interval, which I think that you can do. And then look at the left and right-hand side limits. Left-hand side limit approaching b, which is 1 in this case. Right-hand side limit approaching a, which is -1 in this case. Those equal the function being evaluated there, then it's continuous on that closed interval. Okay. All right, so I'm going to pause the video again, and maybe take some questions. All right, so I think we're ready to finish off the lecture with some important notes or theorems. So, as you might suspect, the scalar multiple, the addition of continuous functions, the multiplication of continuous functions, and even ratios of continuous functions will also be continuous, which makes life really easy because once you have a grasp with like a bunch of like simple, easy to understand functions that are continuous, then if you encounter something more complicated, like you might see that it's somehow some combination of operations between like simple continuous functions, which means that the bigger function would be continuous. So to write this out formally, if b is some real number, again, there's that epsilon, that just means b is a real number. That's all that says. Just shorthand for it. This is R. And F and G are continuous at x equals to c, then the following functions are continuous. So first off, scalar multiplication. So B is a scalar, so B times, oh, are continuous at x equals to c. I forgot that part, important. So the function B times F, continuous at x equals to c. Part 2, F plus or minus G is continuous at x equals to c. Part 3, F times G is continuous at x equals to c. And then finally, part 4, F divided by G. But as we've encountered before, we have to be careful here. We have division by something, and we haven't specified anything about whether or not that could be 0, right? So we have to always be careful and note that when G evaluated at C is not equal to 0. Okay. Okay, so immediately we get all kinds of functions that are going to be continuous at a given point and over all of R, actually. So like some examples would be like f of x equals to, I don't know, like x plus sine of x, right? Like x by itself is continuous on all of R, and so is sine. So the sum is going to be continuous. So yeah, there's just so many more that you can come up with now, right? Okay. Now, we can extend this theorem to one more operation, which is function composition, right? So, for example, well, we have to write out a little bit more. So I guess I'll write it as another theorem. So if G is continuous at C, let's say x equals to C, and F is continuous at x equals to G of C, right? Then all kinds of notation here that's getting messy, but then F composed with G of X, which if you recall from like pre-cal or college algebra, this is just F evaluated at G of X. So if these conditions are met, then this function, this composite function, is continuous at x equals to C. Okay. So that actually probably could have helped us out earlier. Where could have it helped us out? back to the example we had earlier. Let me think. No, I need to make another one. Like, yeah, I'm gonna try to come up with something different because I keep on writing the same things up here. Something like that, right? And maybe we want to like discuss the continuity of that function at x equals to 2, right? So question is f continuous at x equals to 2? Well, this is a composite function, right? So, for example, get the right out of solution. So, maybe I'll use h and g. So, h of x is equal to sine of x, and g of x is equal to 1 over x, right? Then f of x is equal to h composed with g, right? You just plug g into h of x, we get sine of 1 over x, right? And so looking at this statement here, g is continuous at x equals to 2, right? And h is continuous at g of 2, right? G of 2 is what, a half? And then sine of a half is that's going to be continuous there. So that means that we could apply this theorem and say, yes, that function is continuous at x equals to 2. All right, so I think I'll give maybe 1, 2 more examples and then we'll call it a day. So suppose find all x where f of x equals to tangent of x is continuous. This might be, seems like indicative of a problem that you might encounter actually in a textbook or on an exam. Okay, so in order to do that, we need to determine where the funny business happens, if there is any, right? Like, is there going to be ever an undefined x, and where are those undefined x occurring? Now, in order to do that, you kind of need to know some basics of trig, right? So, two things. The sine and cosine function values live on this unit circle, right? So for any given angle theta, that point right here is going to be described by cosine of theta times sine of theta. That point, okay? So the x values come from cosine, the y values come from sine, right? Okay, so you need to be familiar with that. And then next, you need to recall that tangent of theta or x or whatever variable you choose. I'll use theta because I use theta up here. Is equal to sine of theta divided by cosine of theta. That's the definition of the tangent. So when considering where a tangent of x is continuous, look to the definition of what it is. It's the ratio of sine over cosine, right? Now, can there ever be a problem here where there'll be division by something bad? Well, basically, look to the unit circle and find the points in that unit circle where x is equal to 0 and you have a problem with tangent, right? So where would those problem points be? Right here, right? That point is going to have x equals to 0, y equals to 1, right? And then also down here. Right, this is the point 0, comma minus 1. This is the point 0, comma positive 1. And since those points are determined by cosine and sine, at this point there, or that angle there, if we're doing in radians, cosine will be 0, tangent won't be defined there. Right? So, what can we say? Well, anytime tangent isn't defined at a given point, then it can't be continuous at that point, right? So, this is a circle, right? So, from here to there, that angle is pi. To wrap all the way around is 2 pi. Right? So that basically means that we can cut this unit circle into like fourths, right? Or like start dividing it into pieces and figuring out what angles are going to make these, right? So if this is pi, that angle from here to there is pi, then this angle from here to there is half pi. It's pi over 2, right? So at pi over 2, the angle is going to be bad. We'll have division by 0. All right, so let's just start like listing them out. So we see that x cannot equal pi over 2. Okay. So what about this angle all the way around there? Well, here's pi over 2, and then pi, and then we add pi over 2 again, we get what? Right. Or another way of saying that is pi over 2 plus pi, right? If we're up there and we want to like go 90 degrees around, we add pi and we end up down there. Okay. But then we can keep this going, right? If we're down here and we add pi, what's going to happen? Another bad angle, right? So then instead of adding, so if we started here and added 1 pi, we'd end up there. If we add 2 pi, we're back to where we started, right? So 2 pi. But then once we're up there, we can add another pi, right? So again, pi over 2. So add 1 pi, we go down. Add 2 pi, we come back around. Add 3 pi, we go around again, right? This is going to continue forever. We're always going to circle back around and around and around and around, right? So, okay. Well, we at least know something. We know that no problems will occur from here to pi over 2, right? So it looks like from there to there, we're good. But also from there, right? From here to there, we're good. To there, right? You see that? Like not inclusive, like every angle in between, right? It'll be fine in there. There'll be no division by 0. So that angle, like down here, that's negative pi over 2, right? So from negative pi over 2 to pi over 2, we're good, right? Non-inclusive. So these would be like open intervals. So maybe something like negative pi over 2 to pi over 2 is an open interval of values where tangent is good and continuous and nothing funny is happening. Okay? It's a ratio of 2 continuous functions. It'll be fine. But then it's going to be good from here to there, right? Non-inclusive, right? So what are all those values? So another open interval would be pi over 2 to pi over 2 plus pi. Open interval, right? And then we're down here now and we go again. So there's like a pattern that's emerging. Dot, dot, dot. Maybe, no, we could just write it like this. So that you really see the pattern. Pi over 2 again. And then next one's there. So do you see what's happening? The end point of this interval will be the beginning point of this interval. And then the end point of this interval here is going to be 1 more pi than there is there. So it looks like I'm getting messy with my interval notation, but I'm trying to think of like a way to write this to really capture what's going on. What about pi over 2 plus n times pi, comma, pi over 2 plus n plus 1 pi. So what about this right here? For every integer n. What about that? That's like, does this make sense? Is that where that function tangent is continuous? Well, hopefully you understood where x couldn't be, right? So basically what we're doing is we're excluding all those possible x's by not including them in these intervals. That's the start, right? And then I started to notice a pattern, and I tried to write it this way. Now, does this make sense? Well, what happens for this proposed solution to the problem? So n can be any integer. So these are positive and negative whole numbers, right? So what happens when n is equal to 0? What does this interval become? Pi over 2 plus 0, comma, pi over 2 plus pi. But what about positive 1? Well, when n is equal to 1, we have pi over 2 plus pi, and then pi over 2 plus 2 pi. That's exactly what we had over there, right? Dot, dot, dot. We're just grabbing all of those angles that avoid those points. That's all we're doing. Okay. Now, what about the negative ones? The negative ones will still work, right? Like when n is equal to -1,